So welcome. Get my pen. And today we're going to do superposition of standing waves. And big ideas. Big ideas, if two or more waves occupy the same space, they can interfere with each other. They can add constructively or destructively. That's a bit weird if you think about it. So the energy from one wave is occupying the same space as the energy from another wave. And sometimes you get a node. You get no vibration. And that's weird. That's energy cancelling, which is a little bit weird. And other times you get twice as much energy. So it's a strange kind of situation. When a family of waves are reflected back on themselves, those that experience destructive interference quickly die out, while those that experience constructive interference sustain. Musicians talk about sustain on a plucked string. Piano, there's a little key, a little pedal for sustain. Sustain means to continue. When I pluck a guitar string, there's nothing special about the way I pluck it that says this is a 512 hertz fundamental frequency. I just put energy in. That's all I'm doing, putting energy in. And the guitar string somehow responds by trying all frequencies and filtering out all the frequencies apart from 512, and as it turns out 1024, and then 1536, and so on. There's a family of frequencies that it will allow to sustain. And all the other frequencies that are possible, forbidden, or if you imagine them being created, they quickly die out. And you can picture them as quickly dying out because, well, if a crest comes back as a trough, it cancels. So depending upon the picture of the wavelength pattern, I can justify to myself, oh, that thing's going to die and that thing's going to live. And then an instrument such as a taut string, or an organ pipe, they're the two classics, will support a family of waves that are harmoniously related. So what makes the guitar string sound rich are sometimes called the overtones, sometimes called the harmonics. It's those other frequencies than the fundamental frequency or the first harmonic, same thing, that give it a richness. You're kind of not just you're hearing maybe 10 notes, but they're not random 10 notes. They're all related mathematically to each other. They're all factors of the fundamental. And that excites our ear much more pleasingly than if we have either a single frequency, like in a tuning fork. Tuning forks are made so that they give you the single frequency as much as possible. Or unrelated frequencies. So if you had 723 and 697, they would grate. And in fact, there's a whole area of research where people are trying to make more and more annoying alarms. And the way they're finding is if they make an alarm which has a family of frequencies which have prime numbers, so there's no factors below them that can just dial them in. Man, that grates your teeth. That's really awful because it's completely not harmonic. And then two waves with slightly different frequencies will produce a sound that displays beats. We're going to talk about beat frequency. Beat frequency is not a new, well, if I play, say, 500 and 502 hertz, I will hear a tone, a pitch, if you like, which is 501 hertz. So the carrier frequency that I hear is the average between the two. That's interesting. But the second thing is the amplitude of that frequency oscillates. So it gets big or small, loud or soft. And it oscillates with a frequency. The wow, wow, wow has a frequency, which is the difference between those two frequencies. So if the difference is 2 hertz, I'll get a 2 hertz wow, wow, wow. And the sound I'm hearing is the average between those two notes. So I could hear a high-pitch 2 hertz beat, say 12,000 and 12,002, would give me a sound which is 12,001 hertz, which is quite high, but it would have a 2 hertz wow, wow, wow on it. And I could have, 100 and 102 hertz. So I'd hear a pitch which is 101 hertz, but I still hit a wow, wow, wow. So we have the carrier frequency, the beat frequency, and how they relate to the two original frequencies. Okay. We're going to start by superposition of waves. And what we say is when two or more waves move in the same linear medium. Linear just means 2 and 2 makes 4. Okay? When two waves move in the same linear frequency, linear medium, the net displacement of the medium, that is the resultant wave, at any point equals the algebraic sum of all the displacements caused by the individual waves. So here we have a picture. I just took this at random. So here's my first wave. And my second wave caused by a second speaker. Imagine sound. I have one speaker in one corner, one speaker in the other corner. Later on, we'll think about light. Light coming from one slit over there, another slit over there. Any kind of wave system. If you have two sources and they're slightly out of phase, then what will happen is that as I stand here, I'll get a wave coming to me from one speaker, I'll get a wave coming to me from the other speaker, and I numerically add what's ever happening. So it turns out that at this first instant, I have 0 from wave 1, I have a little positive from wave 2, so I get a little positive. But then over here, it's a bit hard for me from now on to kind of line things up properly. But from over here, I have a 0 there, and I have a bit of a negative thing there, so I get a bit of a negative thing there. And here, I get let's see if I can get this lined up. There I get a bit of a negative, and there I'm getting a bit of a positive, and they cancel each other out. I'm just numerically, on my x-axis, I'm just saying, what's this value of x for wave 1? What's the value of x for wave 2? What's the y value for wave 1? What's the y value for wave 2? Add them together. Let's go to the next x value. Y value for wave 1, y value for wave 2, add them together. And I don't know if you can see it, but it's kind of like, if they were perfectly in phase, let's look at that. So if they were perfectly in phase, so there's my first one, and there's my second one. And what I'd get is, I'd get twice. So if that's the normal amplitude, I'd get twice the normal amplitude because that crest and that crest coincide, and that trough coincide. So there I am, there and there. So that makes sense. And if, on the other hand, I had the waves that were perfectly out of phase, then I would get 0 because that crest corresponds to that trough, giving me a 0. That trough corresponds to that crest, giving me 0. And all the guys in between, that 0 corresponds to that 0, giving me 0. Because they're the same shape of wave, they're perfectly matched so that I get 0 for everything. In sound, this would be a silence. In sound, this guy on the right-hand side would be an increase in the volume. In light, on the left-hand side, I'd have what appears to be a shadow, although there's nothing in front of it. On the right-hand side, I get what appears to be a brightness. This twice the brightness. And then in between, I get some mixture of the two. And that's what I'm showing here, the more general case, where I'm in between. I'm not in phase, I'm not perfectly out of phase, I've got some kind of phase relationship. So I'd like you to be comfortable with that diagram conceptually. Consider two waves that have the same frequency, wavelength and amplitude that are traveling in a positive x direction. So one's going to be a sine kx minus omega t, and the other one's going to be a sine kx minus omega t plus phi. Remember what we do about when you don't start off with the proper time, you just put a phase angle in. So all I do is put that phase angle in. I add them together, so it's a sine kx minus omega t plus sine kx minus omega t plus phi. And then I've got to remember a bit of trig. Well, I don't remember this trig, I'll look it up, but I get sine A plus sine B equals 2 cos A minus B over 2 sine A plus B over 2, where A is kx minus omega t, and B is kx minus omega t plus phi. And you shove it in, and you get y is equal to 2a cos phi over 2 sine kx minus omega t plus phi over 2. And I want you to know that equation exists. If I throw it onto the paper and say, hey, this is an equation, which is to do with, I'm not going to just say there's an equation, figure it out. And if I said to you, how does y go with a? Is it linear? Is it inverse? Is it that? So I want you to know it exists. If I give you it, I want you to know what omega stands for. I want you to know what phi stands for, so you could do me a conceptual interpretation of it. But you don't have to remember that equation, because I don't remember that equation. Okay, so back in the day when we had the equation sheets, that was fair game, but not these days. But I want you to know that this exists. So mathematically, that's what we just described. The shape of this curve here, the shape of that curve there, is given by that equation. The resultant wave is the same frequency as the wavelength of the original waves, because they're both the same frequency. So this is another diagram showing what I actually explained to you, as we ran along. We get constructive interference when the phase difference is, well, 0. The example I gave was 0. There's one, and then there's the other. Now let's number these things. So that's peak 1, that's peak 1, that's peak 2, that's peak 2, that's peak 3, that's peak 3. Because here's a weird thing. If I'm in the middle, then do you want to think in terms of water ripples, or do you want to think in terms of sound compressions? It's the same thing. It doesn't matter. Let's talk in terms of sound compressions. Okay? So I get a compression from one and a compression from the other. They take a certain length of time to reach me. I'm the same distance from each source. What happens is, the crest appears with a crest and the trough appears with a trough. Yeah? Because they're in phase. Does that make sense? If I had two people walking towards me and they were marching in step, and they started off marching in step, and it's the same distance to me that arrive in step. Yeah? That's constructive interference. Here's an interesting thing, though. Supposing I go across here, no longer the same path difference. But you know what? Let's count the steps. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 9th step from this guy that's close is coinciding with the 10th step from that guy who's further away. They're still in phase. They're still in step. So I get constructive interference. I don't care which crest and crest or trough and trough. All I care about is the phase difference between them. So I had constructive interference over here where the path difference was the same, but I have constructive interference over here where the path difference is different. Because crest 9 lines up with crest 10. Crest 9 lines up with crest 11. Crest 9 lines up with crest 12. So I get lots of different positions where I get constructive interference. In between, if I go from here, and the same goes on that side, if I go in between halfway, I get 1, 2, 3, 4, 5, 6, 7, 8, 9. And I get 1, 2, 3, 4, 5, 6, 7, 8, 9 and a half. Now they're out of step. As this guy's stamping his foot, this guy's lifting his foot. It's half a step out, half a wavelength out. They cancel because a crest is coming with a trough. And if I go beyond this other constructive, if I go here, now it's going to be 9 and it's going to be 10 and a half. And beyond this one, it's going to be 9 and 11 and a half, and so on. Okay? So what counts is the difference in the path length as a function of the wavelength, because what counts is the phase difference. So the phase difference, I could talk about the phase difference as a half a wavelength, or 1.5 wavelengths, or 3.5 wavelengths. I could talk about the phase difference as, well, if it was half a wavelength, it would be pi radians, because one wavelength is 2 pi radians. If it was 3.5 wavelengths, it would be 3 over 2 of 2 pi radians. If it was 5 over 2 wavelengths, it would be 5 over 2 of 2.5 wavelengths, of 2 pi radians. And I can do the same in degrees. If it's half a wavelength, that's 2 pi divided by 2 pi radians, which is 180 degrees. And if it's 1.5 wavelengths, that's, let's have a look. 1.5 wavelengths is 3 pi, which would be 360 plus 180. Because we get 2 pi going around once, there's the 360, and we got 1 pi left over, so it's another 180. So I can represent these phase differences as fractions of a wavelength, fractions of 2 pi radians, or fractions of 360 degrees. Everybody okay on that? Okay. So here I have two of the extreme examples in this first one. Basically, the two are in phase with each other, and so what I get is, if I look at my equation, I get 2a sine kx minus omega t. So, yay, constructive. And then if I look at these two, I can see it graphically very easily, but I can also see it from the math. I will get 0. Okay? So I'd like you to be able to recognize what's constructive and what's destructive. We tend to talk more about the extremes than we do about the little shades of grey in between. So what we say is, we get constructive interference when the phase difference is an even number of pi radians. So it's even pi rad. It's even half lambda. Even 180 degrees. 1 times 180 degrees, 2 times 180 degrees, 3 times 180 degrees, and all that kind of stuff. I'm sorry, no. Even means 0 times 180, 2 times 180, 4 times 180, 6 times 180, or 0 times pi radians, or 2 times pi radians, or 4 times pi radians, because we're looking at a 0 half wavelengths, or 2 half wavelengths, or 4 half wavelengths. Yep. And on this side, for destructive interference, I want an odd number of pi radians, or an odd number of half lambdas, or I want an odd number of 180 degrees. So this would be 1 pi radians, or 3 over 2, or, I'm sorry, my brain's not where this day. This would be 1/2 a pi radian, or 3 over 2 pi radians, or 5 over 2 pi radians, because that corresponds to a half a wavelength, or 3 over 2 wavelengths, or 5 over 2 wavelengths. You kind of got a decision to make when you're first beginning, and that is, which one of these 3 ways of visualizing it are you going to think about it in? And to be honest, I tend to think about it in wavelengths, and then I'll transfer. So I say, for constructive interference, I want a whole number of wavelengths, path difference, which is an even number of half wavelengths. And for destructive interference, I want an odd number of half wavelengths. And then I can figure out the rest from there. I can convert that to radians, I can convert that to degrees. But in my mind's eye, I'm going, what's my path difference in terms of numbers of wavelengths? If it's an odd half number, it's destructive. If it's an even half number of wavelengths, it's constructive. Yeah? So, we call one in phase, and the other one is anti-phase, meaning perfectly out of phase. In 2-dimensional stuff, let's imagine speakers in a room. So this is showing compression waves and rarefractions, actually. Or we could imagine ripples on water. whichever you like. And I can pick a whole series of points here. Let's just go down this middle line. So let's go. Let's say we're here. I take a picture, and it just so happens that when I get to this first red spot, I have a compression with a compression. Okay? So, I'm sorry, I'm going to, yeah, compression, I have a key somewhere, but I'm going to say compression with compression. And that's going to be, what is that going to be? Constructive or destructive? Constructive. Constructive. If I go a bit further back, then I have a rarefaction with a rarefaction. Still constructive because they're in phase. And if I go further away, I have a compression with a compression. Constructive. If I go over to the side, I have a rarefaction with rarefaction, compression with compression. I didn't draw it, but rarefaction with rarefaction. If I go down here, I get construction with compression with compression. Did I do that? Have I changed? No. Rarefaction with rarefaction. And again, compression with compression. Whenever you get the same with the same, then you get a line of constructive interference. And in between, I get a construction with a rarefaction and a rarefaction with a construction, and this will be a construction with a rarefaction. And then I have the same again. So this here is const, this is dest, this is const, this is dest, and this is const. And this diagram over here is just showing you the destructive bits. I really meant to do it as two different diagrams. So for this destructive bit would be there, there, and there, 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 and there. And the constructive bits are the other bits. Same diagram. Cool. I'm going to try something. So let me just get out of here. I'm going to have to just discard that for a minute. Yes. And I need to just connect a few more videos. Let's have. Let me just see if I can get here to it. If I can't, I can't. But let me just see if I can. Yeah. Okay. So let's just have YouTube Ripple Tank. And I'm pretty familiar with these, so I might be able to see it straight away. Let's have a look. Well, maybe not. Let's have a look. Is that you? No, I'm going to go back because there's one that I particularly like. So let me have a look next. It's kind of a bit old-fashioned, but if I can't find... Oh, I know what to do. I need to go to video, don't I? Video, that would help. So let's have a look. Dum, 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 dum. One more little search just for a second or two. And if I can't find it, I can't find it. Well, I said one more, but is that it? No.
Professor, maybe you should have to type it into actually YouTube.
No, this will be.
Search it up through Google.
This will be all right. I'm going through Google. It's like the one more. I might be just missing it because I'm looking at the pictures. It doesn't matter. I can just pick any one of these, to be honest. But there's a really good video, and it's a historic video, which is why I kind of like it. We'll just pick one of these goofy ones because it'll show some of this stuff and you'll kind of get to see it. So what they're doing now is this machine sends waves, and you can see they're reflecting. They're reflecting. When you get these little crosses, the bright bits are constructive interference. This is like a mirror This is showing the waves bouncing back, and you're getting these patterns. You can definitely see these patterns of, this is a convex mirror. And this is changing the medium. These are actually to do with lights, but you can see there's a definite effect of, it slows down here. You can see there's an angle produced. I'm going to stop this because there's actually, I want to go back, and I want to go just, I'm going to do, yes. Yes, so here's another example.
There are three things that we can measure when we can wave. Wave speed, frequency, and wavelength. Now, wave speed is how quickly a wave travels through a medium or substance. Frequency is how many waves pass a point per second. And wavelength is the distance between two identical points on neighbouring
And I'm going to jump out of here.
Now, these are all related in one equation, that wave speed equals frequency times wavelength.
Okay, so I'm going to jump out of here because that's also not what I want. I'm going to just change the terms I want. YouTube, I'm going to have double slit. Let's see what that gives me. Double slit interference. I'm going to go with that one. So this is the apparatus. It's got a shallow tank. It's got a light source. You see the image on here. You have these little vibrators that kind of go up and down, in phase or out of phase. So it's making the ripples of the water like compression. So here you see there's a bar, here's a bar with an opening. And you see the water ripples come along, but they can't get through the opening, so they go through this middle bit. And strange things kind of happen when they go through the middle. Looking from above, you can see that the energy comes along and it kind of goes through, it's spreading out a little bit, but it's mainly going straight ahead. And then as they bring these things in, can you see, I don't know if you can see it, but let's see. Now they've opened it up, so it's going a wider single slit, means the energy is going much more linearly through. And slowly increasing the oscillation frequency, increase the frequency reduces the wavelength, so we're making it like a smaller and smaller wavelength. And I need to have a strobe on this, let's see it better. And can you see how, look what's happening, you're getting these null points coming in, yes? These null points coming in, where you see there's constructive interference here, and then there's a little bit of, you can see it really well there. You're seeing less constructive interference and so on. Let's see what's going to be next. So now, they have two slits. So that's like two speakers. And they're sending this plane wave in, it's going through these two slits, and then what's going to happen now is okay, so double slits are there, the energy's coming through, the slits are quite small, so the energy kind of spreads out once it gets through the slits. And as they increase the frequency, it changes the wavelength. And what you'll see is, when they go to high frequencies, can you see those tracks beginning to appear? Can you see those? There's a null there, a null there, and there should be some more coming if they can go faster. You see it's becoming there's clearly some tracks. There's a maximum in the middle, then there's dead space, then another set of maximum, then a little dead space, not so clear, and then so on. And as they go higher, these get more and more. That's the kind of game we're playing. That's what's going on. We get in regions of constructive and destructive interference. That's still not the one that I really want, but I'll find the one that I really want and I'll link it on the side because it's a quite informative little video. And I want to stop you, but I don't know how. So go from there, get out of here. So we're back on this. Okay. And I want to go to from beginning. Okay, so we'll go back to here. Okay. So let's do a thing. So two speakers are in phase. They push when they push. They pull when they pull. A listener stands equal distance from each speaker. What will she hear? Will she hear silence because it's destructive interference? Will she hear loudness because it's constructive interference? Will she hear silence because, well, it's not destructive, it's actually constructive interference? Or will she, or will she hear loudness because it's actually destructive interference? So just decide, and then I'll tell you the answer. Just decide. And it's going to be, well, equal distance, they're in phase. That means that a crest is going to arrive with a crest and a trough with a trough. There's no phase difference between the two. Therefore, it's going to be loudness and it's constructive interference. So it's loudness, but it's constructive interference. So B is the right answer on that one. So let's formalize this a little bit and say, well, we have speaker 1 and speaker 2, and what counts is the difference in distance from the listener to those two speakers. Suppose we have two sources of waves that are in phase. Push when they push, pull when they pull. There's no games going on with the speakers. Let us assume that the waves from each source interfere at point P. The path length from source S1 to P is R1. The path difference for the other one is R2. So there we have our two path differences. At one extreme, if the difference in the path between R1 and R2, the path difference, if you like, draw a circle. It's really that distance there. If the difference in the path between R1 and R2 is an even number of half wavelengths, then we will get constructive interference. So it's an even lambda over 2, which is like saying even pi radians. If you get even lambda over 2, or if you want to put it another way, even pi radians, you get constructive interference. On the other hand, if the path difference between R1 and R2 is an odd number of half wavelengths, so we have odd lambda over 2, which is like odd pi radians, then you get destructive interference. Yep.
So the equation you showed us in the beginning, is that how you find the new wave when you're constructing interference?
When you say the equation I showed you in the beginning, you mean that guy?
Yeah.
Oh, that guy's just to get the shape.
Oh, okay.
I'm never going to ask you to do anything apart from interrogate that one. But that is at a given time, where's my pen? At a given time and a given position, that's the y of my combination of the two waves. Yeah. So don't over chill on that. It's do the other stuff. It's look at and see what's. It's really this bit that's the important bit is when you're getting constructive, when you're getting destructive. It is often useful to express the path difference in terms of the phase difference between the two waves. And the phase difference between the two waves is, well, get your path difference in meters. Work out what fraction of wavelengths that is. And for every wavelength, multiply by pi by 2. Multiply by 2 pi. Yeah. We've been doing that. That's what we've been doing. We've been writing down these things at the side. We've been doing that in our heads. But that's the formalization. The phase difference in radians is take the path difference in meters, divide it by the wavelength. That tells you how many wavelengths you've got. And then for each wavelength, multiply by 2 pi. And that will tell you how many radians. Or if you like, multiply by 360 degrees. That will tell you how many degrees you have if you want. That's one of those equations where I don't learn it because I can figure it out. So let's do some of these. Consider the interference of a sound wave. Two sound sources that are in phase. The distance of R1 is 2.8 meters. Distance R2 is 2.2 meters. The wavelength of sound is 0.4 meters. Show the phase difference. So phi is going to be equal to R2 minus R1 over, what was it, lambda. That gives me the phase difference in wavelengths. And I want to multiply it by 2 pi if I want it in radians. Okay? So that would equal 2.8 minus 2.2 over 0.4 times 2 pi. So that equals 0.6 over 1.4 is 1.5 times 2 pi, which equals 3 pi rad. Yeah? And that's what you want me to prove, 3 pi radians. If you prefer, I can say path difference in meters equals 2.8 minus 2.2, which equals 0.6 meters. I can say the path difference in lambda is equal to 0.6 over 0.4, which equals 1.5 lambda. I can say path difference in rad is equal to 1.5 times 2 pi, which equals 3 pi radians. Get the same answer, just in one case I'm kind of like doing it step by step by step, and in the other case I'm doing it using an equation. And this is just to reinforce that. So one wavelength is 2 pi radians, which is 360 degrees. Half a wavelength is 1 pi radians, which is 180 degrees. And a quarter wavelength is 0.5 pi radians, which is 90 degrees. And I just find it convenient. Try and think in one of them. I tend to think in wavelengths and then do the conversion. I wouldn't try and learn all three simultaneously.
What's that little symbol down there?
Which one?
The upside down V.
Oh, that's lambda. That's the Greek letter lambda, and it's basically it's a lazy V, if you like. It looks like that. It's like propped up like that. So, and yeah, okay. Interference due to path difference of different length and phase difference. Let's move this out of the way. Out of the way of sources. So now, if the wave sources are not in phase, we must consider this phase difference in addition to the path difference effect. So let's take the extreme. Anti-phase is push when I'm pulling, pull when I'm pushing. Push when I'm pulling, pull when I'm pushing. My dad was a keen kind of like consumer electronics guy. He grew up at the time of radio and got used to playing with radio sets. And then when TV sets come in, he played with TV sets. He was a furniture sales guy for a long time, and those things were sold in furniture stores. They were like a piece of furniture. So he got used to kind of figuring out how they worked. And in the Air Force, he learned some electronics because he was a navigator, and navigators had to be able to fix the radio if it broke and all that kind of stuff. There was. When I was at maybe 15, 16, stereo was becoming very popular in Britain. If you look back at the old Beatles, the original Beatles LPs, they were mono. They didn't do stereo, they did mono. And then around about 1970, maybe 68, 70, stereo started coming in, and people would go crazy. Because it is, if you've never heard it before, it is quite shocking. And I remember there was one group did this thing where they'd play with it. So they had like this noise of a train, and they had the noise of the train going from one speaker to another speaker. kind of across the room, and people would sit there and go, oh, listen to this bit. And they'd all be pointing to where the train was, you know. It sounds silly now, we're so used to it, but it was like a big deal at that stage. And then if stereo is great, why not do quadraphonic sound? So my dad built his own quadraphonic system. So the needle basically goes like that in a stereo system. In a mono system, it goes like that. And in a stereo system, you kind of get some whittle waddle on it from side to side. And with quadraphonic, there's something else takes place as well. It sounded great. His jazz records would come out really good. And he started playing some of the records that I had, and they were awful. You could not hear the vocals at all. It was like really poor. And these were stereo, but they should have played normally, you know. And then what he realized was it got on one of the speakers, one out of the 4 speakers, he had the wires switched. So rather than pushing and pushing, there was one that was always 90 degrees, always 180 degrees out of phase. And so within the space of the room, it was cancelling out certain frequencies, and they tended to be the frequencies that were more heavily used by the vocals. So huge difference because those 2 wires were backwards. And I kept saying to him, there's something wrong, you can't hear the singer. And my dad said, who wants to hear this guy? You know, like that kind of stuff. So, but it makes a big difference. So now we're going to play with that. We're going to just have them like the wires reversed. So we're going to have a push when we're pulling and a pull when we're pushing. So we say, if the wave sources are not in phase, we must consider this phase difference in addition to path difference. If the total effect is an even number of half wavelengths, the 2 waves add constructively. And if the total effect is an odd number of half wavelengths, the 2 waves add destructively. For me as the listener, it makes no difference. All I say is, do I hear a crest with a trough, or a compression with a rarefaction, or do I hear 2 compressions or 2 rarefactions? What's the phase of what I hear? Previously, I only considered the path difference effect because the 2 were in phase. But now the 2 are out of phase. So I've got to take that into account. So even distance, it's like one starts off half a step in front of the other. So I go, if you like, I go a half, 1.5, 2.5, 3.5, 4.5, 5.5, 6.5. And I go 1, 2, 3, 4, 5, 6. The difference is half a step, half a wavelength. What do I hear? Constructive or destructive? Destructive, even though the path difference is the same, because one of them starts half a step out, it's destructive interference. And so what was constructive becomes destructive. What was destructive, half a wavelength difference. Now, because one starts half a wavelength out, becomes constructive, everything reverses. What was destructive becomes constructive and vice versa. So, okay, so now we have to take that into account. Consider the interference of 2 sound sources that are out of phase by pi radians. I'll put it there. The difference between the 2 distances is 2.9 meters and 2.5 meters. The wavelength is 0.4 meters. Show the phase difference at point P is 3 radians. So I go, okay, well, let's have a look. I have my phase difference at P is equal to my phase difference caused by my path plus my phase difference at the source. Does that make sense? Before, we only considered the path difference because there was no phase difference at the source. But now there is. And I say, well, my phase difference at P is going to equal, well, it's going to be R1 minus R2 over lambda times 2 pi plus the phase difference of the source. So that is going to equal 2.9 minus 2.5 over 0.4 times 2 pi plus pi, which equals 0.4 over 0.4 times 2 pi plus pi, which equals 2 pi plus pi, which equals 3 pi. Or what you could do, if it's more comfortable, is you can say, let's work in wavelengths. So this is going to be, let's look, my path difference is 0.4. So this is going to be my phase difference in wavelengths is going to equal 1 wavelength, because it's 0.4 over 4, plus 1/2 a wavelength, which equals 3 over 2 wavelengths, which equals 3 over 2 times 2 pi, which equals 3 pi radians. So you can think about it in wavelengths when they're anti-phase, they're half a wavelength different, crest and trough, half a wavelength apart, and you work like that. So there's two different ways of thinking about it, and it doesn't really matter which one you do, as long as you're comfortable with that. Questions on that? Okay, I'm going to stop there for take a break of 5 minutes. So let's do a. So that's going to be